Okay, I will start. There's only one around here online lesson, but I will start the lesson in anyhow to get this video of this concept to the Moodle. I will start from a picture taken from one book. There is this kind of situation where there is a car there and there is some crate or box which they want to take away from that car, and they use those kind of cables here so that there are point A here which has three forces which are attacked to that point. The weight of this box, and then those forces that goes along those cables AC and AB, and we know the angles of those cables which they have measured from the horizontal plane, 30 degrees and 50 degrees. And now we want to check what is the forces, what are those forces which are going along those cables, or that those the ropes there. And we know that the weight of this box is 75 kilograms. Let's solve this problem. And I will give a title of this for this example, equilibrium of a particle. And in Finnish, I will write the Finnish version of this title. We may call that in Finnish pisteen or partikkelin tasapaino. Piste actually means a point, and this particle, it is the Finnish version of the word particle, and tasapaino is the equilibrium. And we had this example 1. I will show it again. This kind of problem here. And we are considering here the equilibrium of that point A, this uppercase A here. It has to be in physical equilibrium. That means that all forces which are attacked to that point A, the sum of those forces will be 0, or the resultant of those forces will be 0 or 0 vector. And let's draw a so-called free body diagram of this problem, and we are focusing our view in this small place around, or small space around this point A there. So and it was said that the weight of this box is 75 kilometers. Sorry, not kilometers, kilograms. So we are having here this point A, And then we have three forces. First force is orientated towards the Earth, or the center of Earth. That means downwards, actually. And then there are two other forces which have angles 30 degrees, as you here see from the picture, 30 degrees and 50 degrees. I try to draw a little bit better picture or diagram. Here we have one force, and then we have this 50 degrees force. Somewhere there. So we have forces. These red ones are unknown. We actually don't know what are the forces along AC and along AB. But we may call them force 1 and force 2. And then we have this weight of that grade or box here, and we know that it is 75 kilograms. So this force, I will call that with the uppercase G, and this is 75 kilograms, and to get the value of force, we must multiply that with free fall acceleration with this number. Let's check what is the value of that. (735.75). This is 735.75, and the unit of this weight is Newton, because kilograms multiplied with meters divided by second to the power of 2, or second squared. That is always Newton. I will write it here. 1 Newton equals 1 kilograms multiplied by meters divided by second squares. And then we know those angles there. We have here 30 degrees and 50 degrees. And this is the point A. And this point A is in equilibrium. Means that all forces sum to 0, or when we calculate the resultant of those forces, three forces, we will get the result of 0. So this means that resultant force will be 0 force. And that means resultant X component equals 0 kilonewtons. Oh, sorry, newtons, not kilonewtons. Of course, it can be also kilonewtons, but then then in this example I have the unit of newtons, and then Ry also 0 newtons. And as we did when we calculated the resultant forces, we calculated the x components and oh, sorry. Thank you for telling me. I did not remember to share my screen to my online students. So I will take a little bit backwards. So I'm considering this kind of example here, where there is a box and there are three forces which are connected to the point A in that picture. And the problem is that we want to solve the value or magnitudes of those forces. And we know that here we have this point A. We know that the weight of that box was 75 kilograms, and then we calculated the value of the force or the weight of that box. It was about approximately 735 newtons. And then we started to solve this problem, and we knew that this point A is in equilibrium, so the resultant force will be 0 force. And now when we calculate those resultant force or those components, this Rx, from that picture we can see that this F1 is oriented to the right hand side, so it will be positive, and the x component we get with the help of cosine. So this F1 gets x component by multiplying that we get the x component by multiplying the magnitude of that force by cosine of that angle, which is measured from the horizontal plane. And then there is the other force F2 there, and it is oriented to the left side from the vertical plane, and that means it will get the minus sign in this equation. And again we get the x component by multiplying F2 by the cosine of that angle we see in the picture. And as we saw here, the x component or the x component of that resultant force must be 0, because that point is in equilibrium. So we get an equation here. This is a first equation we find. Let's call it number 1. And the same with Ry. Now we have these F1 and F2, they both are orientated to the upwards from the horizontal plane, so that means that they both get positive sign, and the components of those forces in the y direction we get by using sine 30 and sine 50. So we get almost exactly same as here, but we just change this cosine to sine. So we get F1 times sine 30 plus F2. This is plus because this F2 is orientated to upwards from that horizontal plane. Sorry, sine 50. In the first equation, we did not need that G force there at all, or the weight of that box, because this force is orientated exactly downwards, so it has not any x components at all. It has only y component, and it is downwards, so that will be minus. So we write minus 735.75. I will skip those new units in the equation because we are using newtons in this calculation process, so the results will be also newtons. So I will just write simple number there. And this is also 0, so the y component of the resultant will be also 0. And this is the equation 2. And now we have to solve this pair of equations. I will do that by using Excel this time. But first I will make a little bit changes to this equation, or at least to the second one. I will write this again. We get pair of equations, and I will write these equations a little bit differently, so that probably it is easier to understand how that Excel sheet works. I will write these multiplications here in the different order, so I will write these cosines and sines first, and then after them I write this name of forces. So I get cosine 30 times F1 minus cosine 50 times F2 equals 0. And the same with this other equation, sine 30 times F1 plus sine 50 times F2. And then I move this constant here, this 735. This has nothing to do with F1 or F2, so it is a simple number or simple constant. I will move that to the right hand side of that equation, and the sign will be changed to plus, or that this will be positive number. And during algebra and geometry course, we had this grammar rule when we solved system of equations or pair of equations, and we will use that again. So we will see that with the Excel it is quite simple to solve. Grammar's rule. First we have this. We have to create a determinant D in which we have only these factors in front of those unknowns. So I will pick cosine 30 and sine 30 first in the first column, and then minus cosine 50 and sine 50 in the second column. Let's use then Excel. First I will write those angles there. We have 30 and 50 degrees. Excel uses radians, so it is better to change those angles to radians. And in Excel there is one command which changes the unit. In English it is radians in plural form, but I have a Finnish Excel here, so in Finnish it is radianit. This is the same as radians. So if you start writing RAD, Excel will give you the correct command. And I will pick that 30 degree there, this number here, so that will change the value to the radians. I will check that by using my calculator. 30 degrees, if we divide that by 180 degrees and multiply with sorry, I had something to do with the Teams. So in my screen there is Excel sheet, and here you can see my calculator. 30 divided by 180, and then I multiply that with pi. And this will give me the same value as the Excel gave there. So here is the command radianit, or radians in English version. And then I copy that there, and it changes also that 50 degrees to radians. And then we have this determinant here, the determinant D, and we have cosine equal sine cosine. In Finnish Excel the cosine is the same as in English version. It is exactly the same cosine, and we pick that value there, and I took that 30 degrees or 0.52 radians there. And there is a cosine value, and then sine with the same angle, 30 degrees or 0.52 radians. Well, sine of the 30 degrees, that is exactly one half, 0.5. And then we have this second column here, minus cosine 50, minus cosine 50. So I picked that 50 degree there. And then second row, sine 50, or sine of that 0.87 radians. And then we have a command. Wait a minute, is it in English the same command? I have to wait a minute. I will check that. Probably it is. I don't know if you know, but I will write this in Finnish version first. MDTM matrix determinant this will give us the determinant of these four numbers here. So I started this by writing the m determ, and then I paint these four numbers, and that will give us the value of the determinant of this. Of course, we could also calculate that by hand or with the help of calculator. I will do that to see that this gives exactly the correct one. The determinant of these four numbers, I multiply these to cosine 30 times sine 50, cosine 30 times sine 50 minus, and then I multiply these two, sine 30 and minus cosine 50. And it gives us the same answer as this Excel. This has also more decimals here. So this is the value of this first determinant. I will write the answer here, 0.984, 0.984807, etc. And then the next determinant, we had this pair of equation here, and first we took those factors in front of those unknowns, and the next determinant will be, I will call this dx, or sorry, d1. The name is not so important, but I will use the d1 to express that with this determinant we will solve the value of f1 in this equation. So let's see the determinant here. When we want to use determinants, we are with the help of those determinants, or solve the pair of equation with the help of those determinants. Now we want to solve the first unknown, and the Kramer rule says that we first have to pick these numbers in the right hand side of this equation. So there will be only 0 and 735.7. And I'm so sorry, this is so, maybe I can change this a little bit smaller. Maybe this is too big font there. And the second column in this determinant will be the same as this determinant above. So here I will have cosine 50 and sine 50. And now when we are using Excel, we actually find those values already there, because they are the same as here. So in Excel I necessarily do not need to again write any cosines or sines there. I only can pick those values from that determinant above. So here is the first determinant, and I will take these values or copy these values from here. So now I am solving D1, and we see that the first component here is 0 and the second one is 735. Sorry, it was 75, this decimals, I forgot that 5 there. 735.75, and as I told, these will be the same as here, so I will only pick those there. So I will write equal sign there, and then I pick that value from the cell H1 and just copy this formula, and now it picks the value from H2. So here I have a second determinant, and to get the value of this determinant, I don't need to write any new formulas there. I can only copy this M determ here. I Control C, I copy that, and I Control V, I paint that there. So now it tells us the value of the D1. So that will be 472.930, etc. I will write only 6 numbers of the results in the paper. Of course, in Excel they are in exact form, so no problem. And then the second determinant, which we use when we solve the second unknown, and in this case we copy these values from this pair of equation in the right hand side. I copy these values to the second column. Here I use those values in the first column, but here I take the second column. And then the first column will be the same as here. Here were those first column, the values in the first column. So I will copy them here. Cosine 30 and sine 30. Cosine 30, sine 30. And again, I use Excel to solve that determinant. These values here are the same as here, so I just pick them from the first determinant. Equal sign and click G1. I will copy the value of G1 there, and then I copy this formula, and it will copy the value from G2 there. And the second column will be those. Of course, it would be good if I had these values also in this Excel sheet, but I'm not going to do that right now. So this is the second determinant, and then I again copy this determinant formula there, and that gives us the value of that D2. (637), etc. And now the values of those unknowns. We know the values of determinants, and we can move this a little bit so we can see the answer here. So I will calculate the value of F1 here and F2 here. And this F1 will be, I'll write it here. F1 will be D1 divided by D. And what do we get? We have this equal sign, and then I pick the value of D1 and I divide it by the value of D and press enter. So this will be 480,226, etc. And this has the unit Newton. As I told in the beginning of this example, I dropped that unit away from these equations, but we know that the value of G was in Newton, so the values of the units of these F1 and F2 will also be Newtons. And the same with F2. We divide D2 by D, and in Excel D2 we pick from here and we divide that by this number. D2 divided by D, or in this my Excel sheet, the cell J7 divided by J1. That will give us the value of 647,007, etc. newtons. So now we have solved this problem. Let's take that. Okay, now I will add this Excel sheet to the Moodle, so you may check that if you want to know how I did that. So right now we have solved this problem. We now know that this F1 will be 480 newtons and this F2 will be 647 newtons. And how can we check this? Let's check this by drawing. How do I draw that? I have to think twice and draw once. These values of those forces are right now so good, so I have to. I'm using an extra paper here. I'm checking to get a good picture. Here right now, there will be. Yes, I can draw that on this paper. I have this kind of paper here. The one grid there is 1 centimeter. So I will draw this picture so that this G here, which is orientated downwards or to the center of Earth, it is the value of that force is 735 newtons. I divide that by 100, so I will get 7.35, and that means centimeters right now. So I start by drawing force which has a length of 7.35 centimeters. So that is, here I start, and 2, 4, let's take it like this. Do I have better? Here, wait a minute. I will use this. 7.35, and it will be somewhere here. So I will draw a force which is, or line which has length of 7.35 7.35 centimeters, or approximately 7.335 centimeters. And the next line I am drawing there will be in the direction of this F1. I will draw that line to this point of that vertical line or line segment. So I need to find out the angle. It is 30 degrees. I will use this to find the correct angle. Here we have horizontal plane. I will use a little bit this kind of line here to help understand what I am doing. And I measured it was 30 degrees there. So I will get 30 degrees here and draw the line which goes like this. So this is 30 degrees. And the second one, the second force has an angle 50 degrees measured from the horizontal plane, and I will take that 50 degrees from here. So this is horizontal line here. I will draw that to see that line. And from that I measure 50 degrees and it will be here. So this was measured from it was 50 degrees. The important thing is that these lines are in the same direction as in this picture. We had those. Or I mean that those lines has to be in the same direction as these forces in the problem. And as you see, when I draw this force, which I knew this was known, and then I draw these two lines there, they cross here, and they form this kind of triangle. And this is so-called force triangle, voimakolmio in Finnish, by the way. Force in Finnish it is voima, and well, triangle, we have had this earlier, kolmio. And this line was in the same direction as F1. So that means that this will be F1. And this line was in the same direction as F2. So this part will be F2. And when I measure from the picture the length of F1, remember that in the picture I use centimeters. So when I measure this, I will get, I don't know, maybe 4.7. Maybe a little bit more, but I'm not going to lie. From the picture, 4.7 centimeters. And the next one, F2, will be about probably 6.4. F2 is approximately 6.4 centimeter. So in reality, I have this scale where 7.35 meant 735 newtons. So in reality, we have to multiply these by 100. So in reality, the F1 will be approximately 470 newtons, and F2 is approximately 640 degrees. And as we see here, when we calculated those forces, we got a little bit, both values are a little bit higher than my approximation from that picture. Probably I draw that line too is it too small? I will check, because that will, yes, that should have been a little bit longer, because right now if I check that length, it is 7.3, and it should be 7.35. So that is the reason I got a little bit too low measures from those F1 and for F2. Well, this the diagram, or this kind of checking from diagram, I will try to checking. This is not. This is. I don't think it is so necessary to waste a lot of time for checking by drawing, but many times you can get some kind of vision of those the approximate values by drawing by hand some kind of figure. For example, I may do that again with the seconds. So let's see this here. This force is 735. Let's say that this is 735, and here I need an angle 30 degrees. So here is horizontal plane, and I approximate that 30 degrees is maybe something like this. And then here I need 50 degrees. So let's approximate. Here is horizontal line. This will be 45 degrees, but it is a little bit more, so probably it is like this. This is 50 degrees and this is 30 degrees. And now I can approximate that this is, or from the picture I see that this will be the F1 and this will be the F2. So from the picture I can see that this F2 must be higher than F1. And now we check. Yes, actually it is so. And from the picture I can approximate that the length of F2 is quite near the value of this force, which was 735 approximately. So I could approximate that probably this would be about 700 newtons, and the correct value is 647. And this is approximately maybe a little bit longer than half of that force. So I would approximate that would be maybe for 400 or 450 newtons. So as we see, it is 480 degrees. So with this very easily and very fast method, we may be quite sure that probably we have calculated the problem correctly. If we, for example, let's say that this F1 we could have, we had got, for example, 1000 newtons, and from the picture we can see that this is a little smaller value than the value of this force. So if the calculated value would be 1000, and from the picture we can see that it is way lower than 1000. So probably we have made error in our calculations. Okay. I will take another example. I will skip the piece paper and take the white paper instead. Let's say we have this kind of example. By the way, one notion. I will show again the picture. If I find that picture. Yeah, this was our problem, which we solved right now, and we got the answer. We got the answer that F1 and F2 were 480 and 647, and especially they are both positive signs, positive values. These could be also negative values. What does that mean? That means that if we get positive values, that means that the direction we estimated or approximated in the first picture are correct. So actually this F1 is going upwards or with the 30 degrees to the this side as we draw in this picture. And also this F2 has the correct orientation. If we had got, for example, this F1, if this would have been minus 480 newtons, that would mean that in this picture the orientation of this force is not correct. The correct orientation or direction is to the point A. So the direction of that arrow would be opposite from that picture. And also we can think like that if we have positive values in forces when we solve this kind of equilibrium problem, when we get positive values for those forces, or all forces which get positive value, they are in tension. That means that this, sorry, I will show the picture again. This cable here, or this rope, or this bar here has tension force. So it has tensile force. And also this other one here has got tensile tension. If we got negative values, those bars will be in compression. I will take an example where we get that kind of result. And let's say we have this kind of situation. We have a wall here, and there are, let's think that here is some kind of wall, and then we have this kind of situation. So this is not anymore any cable. These are some kind of truss bars. And then here we have the force going up downwards again in this example. Let's take a simple value for this. Let's say this 1 kilonewton. And the angles here we have, I draw the horizontal plane here. This angle will be, let's say 20 degrees, and this other angle, I will use 2 there, so this will be, let's say that is 40 degrees. And this is again point A, and let's say this is bar number 1, and this is bar number 2. And again we write equilibrium equations. First, the horizontal forces, or the x component of the resultant force. When we have this kind of situation here, I will draw so-called free body diagram, where I will only use those forces. Here I have 1 kilonewton, and then I have these 2 forces there. This is F1 and F2. And those angles. Note the orientation of those forces. I draw them away, pointing away from that point A. The same as I did here. They were pointing away. (20 and 40 degrees). So the x component of that resultant force, we get those. This is vertical line here, and both forces are pointing to left-hand side of this vertical, from this vertical plane, and that means that in this Rx equation I will use minus signs for those forces. So I will get minus, and now I will be a little bit wiser than I was here. I will write it those at first in this kind of expression or form. I write first those cosines and then the name of forces. So here the force 1, it has an angle 20 degrees. So in this x component, I use cosine of that 20. Cosine 20 times F1 and minus cosine, this F2 has an angle 40 degrees, cosine 40 times F2, and then there are no other forces which has components in the x direction. This 1 kilonewton is pointing downwards, so it has no x component. So I get 0 here. And Ry component, we have the horizontal plane here. F1 and F2 are pointing upwards, so they get positive sign, and this 1 kilonewton is pointing downwards, so it gets negative sign. So here we get the same angles, but now signs. So I get sine 20 times F1 plus sine 40 times F2 minus 1 kilonewton again. I will write that we this the unit is 1 unit is kilonewton, so I'm not writing here kilonewton at the end of this number 1. So here we have equation, and when we are again I will use that Excel sheet there. Small I will change move this -1 to the right hand side, so still I need to write this again, because I don't want to, this is better to write this equation in this format, so that you get 0 in the right hand side, so that means that both x component and y component are 0, and that means that the point A is in equilibrium. So I will write this still a little bit modified. So in the second equation I will move that number 1 to the right hand side. So this is our equation that we will use in the Excel. And now I try to find that Excel sheet again. Here is the example 1, and I will copy. Siirrä tai kopioi means in the English move or copy, and I make a copy of that. So I don't need to change those here, but I will have another sheet here. And when I have this Excel sheet here, I can simply make some changes there, so to get this Excel sheet to solve that pair of equations we have right now. The angles here, they in the example 1 they were 30 and 50, but now they are 20 and 40, so I will change 20 here and 40 here. And what about those equations? In the first equation we had, in the first example we had cosine here, but if we watch the equation now, we have minus cosine, so I need to change minus there. How about this? There we had minus cosine, and we also have minus cosine in this equation, so that is correct. How about this? We have sine there, and in this example we have also sine. And here we have sine, and here is also sine. So only modification we needed to do was in the first place here. And the next one, here we had the first equation, right hand side 0. We have also now 0. There we had right hand side 735, but now we have 1, so I will write 1 there. And these values were copied from that first determinant, so I don't need to change those. And also here, these were copies from the first determinant, I don't need to change those. But here I need to change this value to 0. To 1. As I told in the example 1 when I wrote that Excel sheet, it would have been better to have the value of that force somewhere here in the Excel sheet. So I would need to only change that value. No need to change those determinants. But as you see, we have got the answer here. We did not actually need not to do so much when we had the Excel sheet here. So right now we have to, let's check that from my calculator, because if we made error, it is stupid to continue. So I will use this calculator to check menu 371. I can write the equation here. One difference when I compare the equations in the paper and in my calculator is that I will use x and y in the place of unknowns. I could also use F1 and F2, but it is easier to write x and y there, because those x and y I can find from the keyboard. So minus cosine 20 times x minus cosine 40 times y equals 0. Then the other one, sine 20 times x plus sine 40 times y. And then there was, in this calculator, I could write the first equation also. I did not necessarily need to move that one to the right hand side, but I will use the second format there, so we see that we have exactly the same equation. So let's compare those equations. Are they the same? Minus cosine 20x minus cosine, I think they are correct there. And then I press enter and I get these kind of values here. Let's compare. No, I can't say right now. X minus 2 to 3, the same value in Excel, and Y 274. So we get the same answers from the calculator. So probably we can believe that we made this correctly. So we get answer F1 is, note, minus 2.2397 etc. kilonewtons, and F2 plus 2.7. Oh, sorry, you did not see what I was writing. 2.7474 etc. So this means that this F2 has positive sign. It is easier one. We can, well, both are as easy or as hard. This plus sign here means that this force is tension force, and this minus here means that this force is compression force. If we, I will take that Excel sheet away. If we check that problem here, let's think that we have this kind of bars which hang from the wall like this. So they are attacked to this point and this point, and then they are attacked to each other here, and we pull it here, like here. What happens when we pull this? The length of this bar will be bigger. that means that it has a tension force here as we get the result. But when I pull this A downwards, this will be pushed towards the wall. So there will be compressive force, compression in that bar. And this is what we got from the result, or what those signs of the results tells us. So actually in these kind of problems, what do we need to do when we have this kind of examples where we have some kind of problem where we have 1 point and there are 3 or 4 or 5 etc. forces which pull that point there, the point A in this case, and we have to solve those unknown force. What do we need to do? We need to do the same as we did in resultant problems. We created the resultant X, or the horizontal resultant force, and then resultant Y, Ry, or the vertical resultant force. And because the point here is in equilibrium, that means that those resultant components both have to get value 0. If other ones here is not 0, that means that point A is not in equilibrium. It has some kind of velocity. It is going downwards or to the right or up or to the left. It is moving somewhere with some kind of acceleration. But when it is in equilibrium, those forces they add to 0, so that the sum force to this point is 0. And then we always get a pair of equations, and in this case and in this course we solve that pair of equations with the help of Cramer's rule, by making those determinants from those equations. The same method as in algebra and geometry course. And you may calculate or solve those determinants by hand. It's a very simple thing, or not simply by hand, but using some kind of calculator. But of course, I suggest you to practice using Excel. So with this kind of Excel sheets, you may solve those pair of equations. And during a weekend, I will make some new assignments which are concerning this kind of problems. There are probably there will be 4 forces which all in the same equilibrium point, and you have to solve those 2 unknowns, and this is the practice of these examples. But they will be in the Moodle probably, I think, tomorrow probably you will find them. There will be about, I think, maybe four assignments concerning this problem. Yeah. But I think this is enough for today. I started these lessons. There was only one around, and I probably 15 minutes I spoke, and I didn't remember to share my screen. So in the Teams nobody could not see anything. But from the video I recorded, there everything is can be seen. So that is not problem. So, but I'm sorry that in the Teams you could not see that. But probably first one who commented was the first one who saw that there was no anything, nothing in the screen so shared. But I will end today's lessons, and I wish you good weekend, and if you have assignments to do, so please calculate those and solve those problems and send to me, and I will check those also during a weekend, so no problem at all. Next week, I don't remember, probably we have lessons on Friday, at least on Friday, but I don't remember if we have lessons in Wednesday. I'm not sure, but the concept in the next week lessons will be cross multiplication or cross product of vectors, and probably some applications of that thing. And that is the last one we will have, last concept concerning vectors. Then we will move to matrices. Matrices will be a little bit different, I think, easier ones concept than these vectors, in my opinion. But let's end today, and thank you for today's lessons, and have a nice week. Hyvää viikonloppua.